What's the rate of change of f in the x direction at 2, 2? Jennifer, did you get that? Okay. Sarah, did you get that? Come on. Where am I? Did you get it, Sarah? Where am I? Why isn't this moving? Everything we've been talking about lately. Zochi, did you get it? David. This is not an estimation or numerical question. It's a symbolic representation question. Yeah. There. No. Noah. Thank you. Guys, what's going on? It's the partial derivative of x. It's the partial derivative of x at 2, 2. Evaluated at 2, 2. You did know, but you didn't know. There's no other correct answer, right? So yeah, I knew that. Okay, then why didn't you put that? That's the only way to express the rate of change of f in the direction of x at 2, 2. Okay? So then, how much does z change by if x changes by negative 0.4 from 2, 2? You started. Right? Okay, so what? dz equals the rate, the partial with respect to x, times dx, right? This is the meaning of the rate of change. Given any small change in your independent, the resulting change in the dependent is the rate times that change in independent. So this answer would be, the rate is f sub x of 2, 2 times negative 0.04. So that expression would calculate the resulting change in z for a change of x of negative 0.04. Okay? So how much does z change by if y changes by 0.01? John C, did you get that one? Partial with respect to y at 2, 2, yep. M dy now, right? So you got to get the right m, right? So it's the rate in the y direction times the little change in y gives you the little change in z. Okay, so how much does z change if both of those changes above occur? Jake, did you get it?
Yeah, if you just add the f of x expression we did for the second one.
Right. So we got dz would be the change due to the change in x, the change in z due to the change in y, added together. So the total change is going to be the sum of changes, right? Total change is the sum of changes. Okay, so now we're starting to talk about this idea that if you make a change in both variables, that kind of indicates like a single change in a direction, right? So what are we? We're going in the negative x direction here. And then proportionally, so I drew the change in the x direction as 1. Proportionally negative 1. Proportionally, how much is our change in y to that? So if this is my change in x, which was the negative 0.04, but magnified to 1, proportionally, what's my change in y? Up the same amount? Up twice as much? Quarter the amount, right? A quarter the amount. So it's kind of like I have, right, like a 4-to-1 ratio here, right? Of changes. So that 4-to-1 ratio, actually it's like kind of -4, +1, right? -4x to +1. Together, those changes together like indicate a direction from our point, right? So there's this direction. And so rather than say we're going to change x this amount or y this amount, we could say we're going to change some amount in this direction. We're going to change some amount in that direction, which would be changes in x and y. They're in this proportion, right? The change in x will always be -4 times as much as the change in y. See that? So yeah.
Sorry, why did y change up 1?
Because it's 1/4 as much as x.
Oh, still on.
Yeah, I'm still relative to this example, right? I'm still relative to this example. I'm saying first for any change in x this way, change in y is like 1/4. Okay, so then we could talk about just if we were to move along in this direction, keeping the proportions of change in x and change in y in this proportion, then we could talk about a rate of change then in that direction, right? A rate of change in that direction. And so might as well use it here. Okay, and so then we could use then our standard trig angle to mean that direction. So what did I have? So we could say this angle theta is such that the change in x is always -4 times as much as the change in y. Going back to the example I gave you. So these would be in the ratio of -4 x to +1 and y. And so we could use triangle trig to get what that angle would be, right? So this is what this length would be the square root of 17. So you'd have a hypotenuse of square root of 17. And so what would that angle be? That angle would be, you could do tangent inverse of 1/4 or whatever, cosine inverse of -4 over 17, whatever you need to do to get that angle. But there is some angle that indicates that direction where y is 1/4 of x, the opposite of x. Okay? And so then, in order to talk about, so what about the rate of change then? The rate of change then, so let's see, so simply dz in that direction, we said was fx dx plus partial y dy, right? So if we wanted dz, not just the change in z, but the change in z for a change in 1, that would be the rate of change in that direction, right? So if we were to make that change in that direction 1 unit, then the resulting change in z would be the rate of change in that direction. Does that make sense? Okay, so then how do we make that 1 unit? So then what is our dx and dy for the rate of change? So the rate of change in direction of theta would be f of x 2 times something plus f of y 2 times something. So what dx and dy would we have in order to make sure that that resulting change was a distance of 1, and therefore we'd have when we did dz, we'd have the rate of change. So what would those be? What would dx be? So now I'm thinking about how far would I have to go this way and how far would I have to go this way if I sweep an angle theta so that that length right there is 1. right? So it's like we're on the unit circle now. So pretend that this is the unit circle, right? So the change in x would be? No, r is 1. I mean, we want to force r to be 1. So yeah, you had it. Just cosine theta, right? So if the change in x is cosine theta and the change in y is sine theta, doesn't that give us a change in the plane of 1? Because that's on the unit circle. And so then the corresponding, this would be like the change in z for a change of 1 in that direction. So that would be the rate of change in that direction. Does that make sense? Okay, and so then we can write that as the dot product of two vectors, right? Because you have two things multiplied and added together, right? So that's the same as what the dot product of f of x 2, 2, comma f of y 2, 2, dot what? Cosine theta, sine theta. So that's that value then will give you the rate of change at 2, 2, at the point 2, 2, it will give you the rate of change in any direction specified by theta. So this is called the directional derivative, right? And you did like some conceptual practice of that in your web work. And the notation for that is capital D sub u f. So this u then is what? U stands for unit vector in the direction of theta. And that's that cosine, sine. Cosine theta, sine theta is the unit vector in the direction of theta. So then this expression will give you the rate of change, which is a value, right, a scalar, in the direction of theta from that point. So it's the rate of change of f in the direction of u at any point x, y. In this case, I'm showing just specifically for the point 2, 2. So this right here, this vector, the vector of the partial derivatives, so you take the partial derivative of x, take the partial derivative of y, put it into a vector, that's called the gradient. The gradient vector. It's the vector of the partial derivatives. It's the vector of the partial derivatives. When you take the dot product of the gradient and the unit vector indicating direction, you get the rate of change at the point that you're at in the direction of that unit vector. It really comes from this whole idea of a change in z is, right? So if you work our way backwards here, it comes from the idea that the change in z is the derivative times the change in x plus the derivative times the change in y. And then we force the dx and dy to give us a resulting change of 1. And then we get the rate of change. Okay, so let's... So now we're talking about pick a direction, pick a point on the function, maybe. Here we go. Pick a point on a function, pick a direction, and we're going to be able now to know what the rate of change of that function is in that direction. So let's talk about that in terms of a 3D surface, right? So anyone have an idea what the surface is? What's it? Paraboloid, yeah, paraboloid. And if this actually opens, you don't know if it's opening up or down because I haven't given you any values, but this actually opens down. I'll just show it in the first octant there. Okay, it opens down. So now we're going to take this whole thing about directional derivative and kind of apply it to the surface, right? So we're talking about the contour plot, but what about the surface? Okay, so we have this point, and that's this point 2, 2, and so that. So let me give you the actual paraboloid here. It's too small to read. So this is z equals, or f of xy equals 1/2 x squared plus 1/4 y squared negative plus 4. So those are both negative. It's opening downward, right? So these should be both negative. So negative 1/2 x squared minus 1/4 y squared plus 4. Can you read everything I wrote there? So that's this function, and that's the function you were looking at with the contour plot. And so we're focusing on the point 2, 2. And so the z value is what you would get when you plug f of 2, 2 would be the z value, and it would then give you this point on the surface. And then this is this point 2, 2, just xy 2, 2 in the xy plane. Okay, so we're going to think about having, now for whatever given point we have, we're going to think about having a circle in there. And so then you gotta, in the XYZ space, everything is turned a little bit, right? So now this is showing the direction of positive, both are showing the direction of what, positive I or positive X. And so then we want to think about changing the direction. Okay, so, and then saying, all right, if I have this direction right here, let's say this one over here. If I have this direction right here, what's the rate of change of f in that direction? What's the rate of change of f in that direction? Or let's do this. It's just small angle theta. Let's just do like pi over 6. I lied, pi over 3. So here's pi over 3. So we're at that point 2, 2, and we want to know what's the rate of change of f at 2, 2 in the direction of pi over 3. So first of all, before we calculate that, can you say anything about that? Can you make a prediction? Probably negative. Probably or definitely? Definitely, right? So if you take a little step, if you take a little change in that direction of that blue vector right there, what's z going to do? It's going to decrease, right? So if we go in that direction, z is going to decrease. And the question is, given a little change in that direction, how can we calculate the amount of decrease in z? Well, we need the directional derivative, right? So let's just go ahead and do it. So I'm saying that this is pi over 3. So we're talking about the directional derivative, u, f. So first, let's just write it out generally, because I keep focusing on 2, 2. So let's write out the formula for the directional derivative for any unit vector u in the direction of theta and any xy. So could we write that out? Could we write out a formula that will calculate the directional? This isn't a calculator problem. There's nothing to do with a calculator here. So could we write out, so now forget about the pi over 3, forget about 2, 2. Could we write out just generally what the derivative in any direction u at any point xy would be. Could you do that? So the gradient dot the unit vector. Okay, and so now for this function, what is that?
So I've got the gradient as f subscript x at 0.22.
Okay, so now I'm removing us from 2, 2 and pi over 3, and I just want to get a general formula for the directional derivative at any point xy and in any direction. Is that, yeah, Trevor?
Would it be
Negative x,
comma negative 2y,
negative 2i.
dot product of cosine theta, sine theta.
Did you get it? Yeah, just a little error. 99 out of 100, Trevor. Is that better?
Yeah, you're right.
Yeah. Or we could write that out this way. So we could write negative x cosine theta minus 1/2 y sine theta. Actually, write the dot product evaluated. So what does that give us? That gives us the rate of change at any point x, y in the direction of theta. Will give us the rate of change. So now, what is the rate of change at 2, 2 in the direction pi over 3? What is the rate of change at 2, 2? So this would be du f of 2, 2. In this notation? Yeah, normally not. You just, yeah, so you could say, I'm not sure. I'm sure different people do it different ways. But if we're getting a number, then you have to know it, yes. But it's not indicated in that notation, like as an argument. Remember your cosines and sines? I picked pi over 3 for, see if you remember. Cosine of pi over 3 is 1/2. So this would be negative 2 times 1/2 minus 1/2 times 2 times square root of 3 over 2. And so what does that all come out to be? Negative 1 minus radical 3 over 2. Was our prediction correct? That's certainly negative. So that's the rate of change. And I can show you that here. No. Yeah, sure. So it's like, remember, so if I took a tangent plane there, and I put it, I slice this thing in the direction that we're picking, then it would be what? It'd be the slope of that contour right there, right? So this, right there at that point, the rate of change is this negative 1 minus radical 3 over 2. Or, so that's showing it also. So we just found this rate of change in the direction of pi over 3 of the surface F. Okay, so does the basic premise make sense? Okay, so let's develop this a little bit further. So we're talking about the derivative in the direction of theta. We know that that's the partial of x times cosine plus the partial of y times sine. And we made that into vectors and made it into a dot product. And we're about to see why making it into a dot product is really useful here. Okay? So this is the gradient. And the gradient you'll see as a, what is that thing? Is there a name for that? It's like an upside down delta, but it means the gradient of f. And the gradient of f is a vector of the partial derivatives. Okay, that's what you have to remember. The gradient of f is a vector of the partial derivatives. the vector of cosine and sine is our unit vector in the direction that we want to find the rate of change. And so it's the directional derivative, okay, the directional derivative. That should just be xy. I don't know why I have that. This should just be the order pair xy. Meaning that your independent variables are still x and y. But then you also have this third argument of the direction. So that's just be xy. Okay. Okay, so if it equals the dot product of the gradient and the unit vector, then we have another way to express dot product. So what is it also? What's another way to express that dot product? Do you remember? So far we're looking at dot product this way as the product of the corresponding components added, but then we had another way to, yeah.
Isn't it magnitudes times cosine theta?
Okay, so the magnitude of
Each gradient times magnitude
right.
of the unit.
Product of the
times
magnitudes
cosine.
times cosine will be times cosine of theta. Is that right? Almost. There's something screwy here that we got to account for. So yeah, product of the magnitudes times the cosine of what? The angle between the vectors. Okay? So is that theta? No, that's a different angle, right? Theta is our standard trig angle swept counterclockwise from 3 o'clock. So that now, we want to call it something different because now this is the angle between whatever the vector, the gradient is, and our unit vector. Make sense? So we don't want to call it theta because theta is our standard trig angle. What the direction we want to find the rate of change is. This is the angle between angle measure between the gradient and so yeah, when you write the gradient, you want to write it with a vector over the top because it's a vector. But in print, it's just bold. Bold means vector. Okay. So, and what's the magnitude of the unit vector? 1. So it's just really the magnitude of the gradient times the cosine between them, right? So if the magnitude of the unit vector is just 1, then we can simplify it this way. So now this form of the directional derivative allows us to answer some questions. If we're thinking about there's a different rate of change in all directions, right? If you change the direction, now you've got the surface, and you think there's a different rate of change no matter, depending on which direction you go. That kind of begs a question, right? What question does it kind of beg? It's a different rate of change for every direction. What's that? Okay, what's the orientation of the gradient? Okay, yep. Or what about in terms of rate of change? If there's a whole host of rates of change as we go around, what might we be interested in of those rates of change?
Where's the highest?
Yeah, the biggest rate of change, right? So where's the rate of change the biggest? So what's the maximum value of the directional derivative? There's got to be some direction that's going to result in the greatest inclination of the surface, right? Or the greatest rate of change. Right, he's all over it. He's a step ahead of me. Okay, so how are we going to maximize? So what we want to do? We want to maximize the value of this. In order to maximize the value of this, so this is set, right? This can't be changed. given a point, given the function and a point, that's vector is set. So how do we get this to be as big as possible? We get cosine alpha to be 1, right? That's the biggest cosine alpha can be. So then the biggest value of the directional derivative is going to be the magnitude of the gradient at that point, because that's where cosine alpha equals 1. Yeah?
I'm sorry, I'm confused. Why do delta, sorry, is it napa f and u not always point in the same direction? I thought they, by definition, did.
No, we choose you. You can be any angle from 0 to 2 pi. We choose you, and then we say we want to find the rate of change in that direction. Because that's the cosine theta sine theta. We're choosing that. We're choosing which direction we want to go, and then say, here's the rate of change in that direction. The gradient it'll be the partial derivatives evaluated at the point in question. That's a fixed vector. So that's a fixed vector. And then we're going to choose in terms of which direction we want the rate of change. Is it better? Does it make sense? So to get the maximum value then of the directional derivative, it's going to be wherever cosine alpha is 1. And then that value of the directional derivative will be the magnitude of the gradient. Okay? And then what about the direction? In what direction alpha is the directional derivative maximized? So what does it mean for cosine alpha to be 1? It means that alpha is 0. So which direction are we going to point u to get that maximum derivative? We want alpha to be 0, so we're going to point it in the same direction as the gradient. So we're going to make u, if we want the maximum rate of change, we're going to make u in the direction of the gradient. And when u is in the direction of the gradient, we're going to get the maximum rate of change of all u's, of all going all the way around. All right, so in our example, the F example that we've been working on, I want you to find the direction and magnitude of max rate of change. So F. Fxy was negative 1/2 x squared minus 1/4 y squared plus, what did I say? 4? I want you to find the magnitude at 2, 2. So at 2, 2, find magnitude and direction of greatest rate of change. All right, let's start with direction. Who has the direction of the max rate of change? Andrew. So tell me, yeah. -2, -1. So we're talking about the direction. Do we need to make it a unit vector? No, we get a unit vector that has the same direction, right? So yeah, so we could do, -2 over radical 5, -1 over radical 5, but we don't need to. So so what quadrant is that in? What quadrant is that pointing? -2, -1. Third quadrant. So what is we saying? We're saying that x is twice, the change in x is twice the change in y, right? So the ratio of change in x to change in y. Now look at the picture. Does that make sense? Along that blue plane, does that look like maybe the direction of steepest ascent, right? Max rate of change going up the surface, right? Best view of this is that a good view? Too dark. No, it's good. Okay. And then what is the max rate of change? So that's the direction, the gradient, and then the max rate of change is, or that rate of change in that direction, radical 5. Magnitude of the gradients, right? Magnitude of the gradient, radical 5. Okay, so I'm showing that over here in the contour plot. What do you notice about what's going on here? So here's that direction. For every 2 you go left, you go 1 down, right? That's that direction. Notice anything about the contour plots? Let me highlight that. What's orthogonal? Do you see that? Do you see that the contour line that we're on right now, that direction of max rate of change is orthogonal to contour lines? Why does that make sense? Why does that make sense? And why do you want the shortest distance from one line? Yeah. So the fastest change in z will be to get to the next higher z contour line. You're going to walk directly towards it, right? And that would be orthogonal to it. That would be orthogonal. By walking orthogonal, it's like you're climbing in z the fastest. Okay. So now we can go through that whole thing again, and we can say, what's the greatest negative rate of change? So we got the greatest positive rate of change is the direction of the gradient, and its rate of change is the magnitude of the gradient. What about the greatest negative rate of change, or the least rate of change? Would it be an exactly, yeah. No, the greatest negative rate of change. The greatest negative rate of change. Yeah. Exactly in the opposite way. So if you want max descent or max negative rate of change, you're going to do in what direction? You're going to do the direction of the opposite of the gradient and the magnitude. So that's the direction. And the magnitude would be? Just be the opposite of the magnitude, right? It's going to be negative of the max. So I could actually show that. And what about the relationship between? So this would be what? 2, 1. So now this would be in the direction. There we go. This would be in the direction 2, 1. What about the relationship between the contour line and the unit vector? Still orthogonal, right? Still orthogonal. So now it's like we're heading in the direction to get the maximum downward change in z. So we're going to go perpendicular to that contour line to get to the next contour line as fast as we can, right? The shortest distance to get to the next contour line will give us the maximum decrease in z. So what about 0, right? So what about if we've got all the rates of change between this most negative to this most positive, then somewhere in between there has to be 0 rate of change. So we can go back to our formula. How are we going to get 0 rate of change if it's the magnitude of f, what, cosine alpha? How are we going to get 0? Alpha is going to be pi over 2, right? Alpha is going to be pi over 2. So that's going to equal 0 when alpha is pi over 2, or 90. Or 3 pi over 2. If we're taking our domain of the unit vectors to be 0 to 2 pi. So where's the first? So here's theta equals 0. So where's the first time that we get 0 rate of change? And look at the trace on the, so here's that plane cutting in that direction. Is it showing 0 rate of change? Close? Let's see, can I do better? There we go. That's good. So you see that curve on the surface is showing 0 rate of change. And this would be alpha equals pi over 2. Alpha equals pi over 2. The angle between them is pi over 2. And notice what's the relationship between that point and the contour line? Tangent. So it'd be like you're walking along the contour line. Z isn't changing. 0 rate of change. But then there's another one, right? Alpha equals 3 pi over 2. And that would be, there's another place over here. That's the closest I can get right there. So now this one pointing in the fourth quadrant angle, also giving a rate of change of 0. You can see it right here. This is for that angle between the vectors of 3 pi over 2. Also, you're walking along the contour line, so your rate of change is 0. So the direction of the gradient gives max rate of change. Pi radians to that gives least rate of change. And then orthogonal to those two is 0 rate of change, both directions. Right? So pi over 2, 0. 3 pi over 2, also 0. Okay. Web work for Friday.